Have you ever stopped to think about how you compare things in the world? That's exactly what a ratio is, a direct comparison between two quantities. Whether you're comparing the number of boys to girls in your class or checking the ingredients for your favorite smoothie, you're using ratios. The core idea is simply showing how much of one thing you have relative to another. A ratio is simply a way to compare two different things or amounts. Think of it like comparing the number of basketballs to the number of soccer balls on a gym shelf. It's a fundamental idea in math that lets us understand the relationships between quantities. When you see a ratio, it's telling you, for this amount of X, you'll have this amount of Y. We use ratios constantly, even if we don't realize it. If you're following a recipe to bake cookies, the ratio of flour to sugar is crucial. A ratio just provides a clear mathematical comparison. It shows how much of one thing there is compared to another. The Common Core standards specifically ask you to understand the language of ratios. You won't always see a colon. Instead, you'll see words like 2, as in the ratio of basketballs to volleyballs is 4:1. You'll also see for every, such as for every 2 dogs at the park, there is 1 person. And finally, you'll see per, often when talking about speed or price, like 25 miles per hour. Being able to translate these phrases into a mathematical comparison is step 1. Once you spot the ratio language, you can write it down in one of 3 ways. First is the simple word form, using the word 2, like 5:2. Second, and most common, is the colon form, 5:2. And third, you can use the fraction form, 5/2. Remember, even in the fraction form, we're still talking about a comparison, not necessarily division. You need to be comfortable switching between all 3 of these forms as they pop up everywhere. It's time to clear up the biggest confusion, the difference between a ratio and a fraction. A ratio is a part-to-part comparison. If you have 3 red shirts and 5 blue shirts, the ratio of red to blue is 3:5. A fraction is a part-to-whole comparison. The total number of shirts is 8. So the fraction of red shirts is 3/8. Ratios compare groups to groups. Fractions compare a group to the total. Let's apply ratios to something you see every day, your school supplies. Imagine you have 5 pencils and 3 pens in your pencil case. If someone asks you for the ratio of pencils to pens, you list the pencils first, making the ratio 5:3. This is a classic part-to-part ratio. Now, if the question is switched and they ask for the ratio of pens to pencils, you simply reverse the order to 3:5. The objects and quantities stay the same, but the comparison changes based on the order the items are named. Ratios are a big part of how we look at team makeup in sports. Let's imagine a basketball team has 2 centers and 10 guards. The part-to-part ratio comparing centers to guards is 2:10. We can also easily find a part-to-whole ratio here. If you add the 2 groups, 2 plus 10, you get 12 total players. Therefore, the ratio of guards to the total players is 10:12. You can see how one ratio compares 2 specific parts, while the other compares a part to the entire group. Seriously, the order of the numbers in a ratio is crucial. If I tell you the ratio of cats to dogs at the shelter is 4:1, that's good news for cat lovers. It means there are 4 cats for every 1 dog. That's very different from the ratio 1:4, which would mean 1 cat for every 4 dogs. Always pay close attention to the question and which quantity is listed first. That quantity's number must be the first one in your ratio. If you mix up the order, your ratio is incorrect. The ratio of A to B is a completely different relationship than the ratio of B to A. Ratios can be written in many different ways while still representing the exact same relationship. These are called equivalent ratios. Think about buying soda. A 6-pack and a 12-pack both contain the same product, just scaled up. We find equivalent ratios by multiplying or dividing both sides of the ratio by the same factor. This process, known as scaling, is exactly what you do when you simplify or find equivalent fractions. Let's practice scaling down or simplifying a ratio. Imagine a class with 12 boys and 18 girls. The initial ratio of boys to girls is 12 to 18. To simplify this, we need to find the largest number that divides into both 12 and 18, which is the greatest common factor, or GCF. That number is 6. We divide both parts by 6. 12 divided by 6 equals 2, and 18 divided by 6 equals 3. Our simplified or equivalent ratio is now 2 to 3. This is the fundamental relationship. It tells us that for every 2 boys, there are 3 girls, and it's a much cleaner way to state the comparison. Ratios are especially important in cooking and mixing. Let's look at this example for making pink lemonade. You mix 4 cups of water with 2 cups of pink mix. That's a ratio of water to mix of 4 to 2. This ratio can be simplified to its lowest terms. We can divide both 4 and 2 by their GCF, which is 2. This gives us the equivalent ratio of 2 to 1. This simplified ratio tells us the basic comparison. You need 2 parts water for every 1 part mix. It's much easier to remember and use this 2 to 1 ratio no matter how big or small of a pitcher you want to make. While simplifying a ratio means scaling down, sometimes you need to find an equivalent ratio that is much larger. You need to scale up. Think about that small paint example again. If you know the perfect color is a 1 to 4 ratio, but you need 10 times the amount of paint, you need to scale up. To scale up, the rule is simple. You multiply both parts of the original ratio by the exact same number. If A, B is your basic ratio, multiplying both A and B by 10 gives you an equivalent ratio that's 10 times bigger. This process is how companies create large batches of products and how builders figure out material needs for bigger projects. Let's work through a practical problem on scaling up. Suppose you found the perfect shade of gray paint, which requires a red to white ratio of 1 to 3. Now you have a much bigger project and decide to use 5 full cans of red paint. How many cans of white paint do you need to keep the color exactly the same? We look at the red part of the ratio, which is 1. To get from 1 to 5 cans, we multiplied by a factor of 5. Since we must keep the ratio equivalent, we multiply the white part, 3, by that same factor. 3 times 5 equals 15. So you need 15 cans of white paint. Your new equivalent ratio is 5:15. When you have to find many equivalent ratios, especially when solving larger word problems, a ratio table is the perfect tool to keep things organized. It's essentially a simple chart where each column represents one equivalent ratio. For instance, if you're tracking how much paint you need, you might have one row for the red paint amount and a second row for the blue paint amount. Ratio tables are great because they help you see the relationship clearly and quickly identify the multiplication or division factor you use to scale from one equivalent ratio to the next, making it much easier to find any missing values. Let's put the ratio table into action with an example. Suppose the ratio of time you spend studying to time spent watching TV is 3 to 1. The table starts with those numbers. Now, if you study for 12 minutes, how much TV time is that equivalent to? Look at the table's study row. To get from 3 minutes to 12 minutes, you had to multiply by 4. That's your scaling factor. You must do the exact same thing to the TV row. We multiply the TV minutes, 1, by 4 as well. 1 times 4 equals 4. So 12 minutes of studying is equivalent to 4 minutes of TV. The ratio table helps us quickly find that missing value. It's important to be able to tell the difference between part-to-part and part-to-whole ratios. A part-to-part ratio is what we've mostly been dealing with, comparing two separate groups, like dogs to cats or pencils to pens. A part-to-whole ratio is when you compare one specific group to the entire total. For example, the ratio of dogs to the total number of pets. To find the whole, you always just add the parts together. If you have a 2-to-3 ratio of fiction to non-fiction books, the whole is 5. So the part-to-whole ratio for fiction books is 2-to-5. Knowing the whole is key for solving more complex word problems. This example requires us to use the total number or the whole to solve the problem. The ratio of soccer players to baseball players is 4-to-5. If we know there are 36 total players in the league, how many are soccer players? First, find the total number of parts in the ratio. 4 plus 5 equals 9 total parts. Next, we divide the total number of players, 36, by the total parts, 9, to find out how many players are in each part. 36 divided by 9 equals 4. That means each part of the ratio is worth 4 players. Since soccer is the first part, 4, we multiply 4 times 4 equals 16. There are 16 soccer players. This technique is a fantastic way to solve problems where you are given the total number. A super important concept related to ratios is the unit rate. A unit rate is a special ratio where the second quantity is always 1. Think about things you talk about every day, like speed, miles per hour. That's a ratio of miles compared to 1 hour. Another common example is price. You look for the price per 1 pound of fruit or dollars per gallon of gas. The language per or each often signals that you are looking at a unit rate. Finding the unit rate is often the easiest way to make comparisons and find the best value. Let's look at how ratio language shows up in everyday sentences. It's all about recognizing those key phrases. When you read a recipe that says, "For every 2 cups of sugar, you need 3 cups of flour," you immediately know the ratio is 2-to-3. If a problem states, "The ratio of blue to yellow is 5-to-1," the colon form is given directly. Or if a news report mentions, "We have 4 teachers per 100 students," the word per quickly tells you the relationship is 4-to-100. Being able to translate these different verbal cues into the standard A to B ratio form is a crucial skill for solving any ratio problem. Let's finish by putting all these concepts together with a final challenge. We've learned that a ratio is just a comparison. Imagine a perfect drink mix, where the water to syrup ratio is 5-to-1. That's 5 parts water for every 1 part syrup. Now for the question. If you use 20 ounces of water, how much syrup do you need? Think about how you got from 5 parts of water to 20 ounces. You multiplied the 5 by 4. 5 times 4 equals 20. You must apply that same factor to the syrup part. So 1 times 4 means you need 4 ounces of syrup. The new equivalent ratio is 20-to-4. Keep an eye out for ratios like this. They're everywhere in your daily life.